of gravity. So we have some works have been published in last years about this topic. So I will present a summary about it we have been working. And first, I will do some introduction about this topic, and after I will present the basic equations regarding the model of gravity, the alternative gravity we are using, and about the compact stars we are dealing with, which is the neutron star. So after that, I'm going to talk about the Python program we use to model this kind of object, and discuss all the results we have been obtaining. So we know that there have been a lot of proposals for alternative theories of gravitation, and they are modification of the general relativity in general. So we have the so-called teleparallel theory of gravity, and this is a theory which is equivalent to GR, but instead of using the scalar rich R, we have the torsion scalar T. It's the basic difference. So and you don't use the metric G mu nu, for example, and use the tetrad. We have another dynamical variable. So we have the basic theory, and we can do modification. We can make modification on this theory to have this alternative gravity. So we can do this change in both GR or teleparallel theory, and build these models of gravitation. So, for example, if we add nonlinear terms in curvature R to GR, we have the so-called F of R models. And on the other hand, if you do the same thing, but consider the Lagrangian density as a function of the torsion scalar T, we have the F of T models. And there are some works in the literature talking about this topic and the application of these alternative models. And in the cosmological, in astrophysical scenario. So it's a topic, a very important topic, and there are a lot of results in this lately. So, how to model spherically symmetrical objects? So we are working with compact objects. So, for example, neutron stars. So you have to know how to model this kind of object. So we use the Thoma-Oppenheim-Volkoff. Hereafter, I will say just TOV equations, and there are these equations are derived from the theory that you are considering. So you are using some theory, some model, and you can derive these equations of motion for this kind of object. So besides that, you have to consider an equation of state. So you can use these 12 equations and the equation of state, which is describing this object, this compact object, and you can model these stars. For example, in my case, I was working with neutron star. So with that, we can determine a lot of things, and especially the maximum mass allowed for a neutron star. Thus, if we are dealing with different gravity model, we are reaching different maximum masses. For example, in GR, we have the maximum compactness of a spherical star. We call this Butch-Down limit. So we have this relation, and the maximum compactness we have is in GR is 4 over 9 in geometrical units. So we cannot have this kind of object with compactness more than that. So we have some problems because there are some events, astrophysical events, like the coalescence involving black hole that we all know, involving a black hole and another compact object. But this second compact object might be a neutron star, but with a high mass. A higher mass than the GR can predict, or a low mass black hole. So is interested to deal with theories which can predict neutron star with more compactness. It's maximum compactness which is higher than this from GR. Okay, so now I will present the basic equations I have to deal with to model this kind of stars. So as I said, the dynamical variable in this kind of models with torsion is not the metric, but the tetrad. So HA mu. But there is a relation between this tetrad and the metric G mu. Given by this relation, and since we want to describe spherical stars, we can use the spherical symmetric metric. So to model this. After that, we can choose a tetrad. So this topic in specific is a very polemic one because when we are dealing with torsion models, we have to choose carefully this tetrad because there are some of them that could bring problems and not describe physically in an acceptable physical way the situation. So there are some problems in the choice of this metric. So the metric chosen here is that one, and that is we can say is a good tetrad for the purpose here. And the torsion tensor can be built from the antisymmetric part of the connection. So in GR we have this part is zero, but here in torsion models we have this antisymmetric part, null. We have another quantity, we name it contortion, and we can write with this, from this contortion, a useful tensor, and from this tensor we can write the torsion scalar, in fact, T. So it's not so difficult to reach this equation 7, who is the expression for the torsion, the scalar torsion. And this is important because if you want to add some nonlinear terms to the basic theory, you have to add the terms with this kind of expression T. So, for example, we have the teleparallel model, which is we have only the torsion here, the linear term, but if you want to have an alternative gravity, we have to add some additional terms. So we have here an arbitrary function of t, where t is given by 7, and we have the Lagrangian density of matter fields here. And we can do the calculations and obtain the equations of motions by varying the action. So doing this, we have these equations here. They are not very, how can I say, simple equations compared to GR, but there are some advantage, because when you compare this to the F of R extensions, the equations are simple. So here we have this FT, FTT, for example, and these are the partial derivative of the function we are choosing here. And there is a misprint here, is the second derivative of F. So the first term is given by an isotropic perfect fluid with pressure P and energy density ρ. So we can choose the form for F of t in the way we want, but it's common to begin with the simpler form. I don't know, but the simpler form we can think is add a quadratic term on t. So this c is an arbitrary constant, real. And we can note that if we set c equals 0, we have just t, the linear term, and we recover the teleparallel equivalent to general relativity. So that's a way to check our results, because we are going to be obtaining a lot of expression, and we can just make c equals 0 and compare if the results we are expecting. Oh, my chair. So after a lot of manipulation, this requires a lot of work, analytical work, and we have used Maple and Mathematica to do that. We can write the difference equation for P, B prime, and A double prime in terms of R, ρ, A prime, and B. Remember that A, B are the functions which appears in the metric. So we can write these difference equations here in terms of these ones. And I will put here some of them. For example, this is the expression for the pressure. And here we have the expression for B prime. And there is another one. There is the expression for A double prime. But this is an insight we had, because if we use the A double prime, the calculation, even with Python program, was very hard to perform. So we realized that if you use, instead of this difference equation for A double prime, the conservation equation, the calculation become much easier. And there are some works in the literature which deals with it, using the for example, A double prime, and they must to perform some perturbative calculation or approximation to deal with the calculation, because they are hard. So making this, the calculation becomes very easy. Okay, so we have a system of differential equations, and now I'm going to present how to deal with these equations and how we did to obtain the results from that. So we have the system of difference equation, and we have now to choose an equation of state to describe the neutron star. in this case. So additionally, the system of difference equations, we have to have a form to calculate the mass, because we are interested in the mass of the star specifically. So we have this form to calculate the mass. It's the form used commonly used by general relativity to calculate the mass. There is a lot of discussion about this. I have a paper just talking about this choice to calculate the mass, but it's a long subject to add here. But it's an open problem. We can say that, but you can use that for now. And we have to choose the equation of state, because we have to choose a way to relate the pressure and the density energy inside the star. So we have two options here, and the first one, and the simpler in general, is the polytropic. So we can use that for a lot of situations, astrophysical situations, and for neutron star you can use two. It's a simple and it's a good description and simple for the compact object, and you can use to compare some alternative theories, theories of gravity. This kind of equation of state is given by this equation 14. Whose zero is the rest mass density, K is a number, polytropic gas constant, and N is the polytropic index. On the other hand, we have the realistic equation of state, which is more complicated, if I can say that, equation. And they're more realistic, that's what the name is that, and it's constrained by nuclear physics and observation, so it's more describing better the reality. Okay, so the next step is perform the integration of the set of the difference equations for a given EOS. We have some papers doing that with polytropic and also realistic ones. So we built a program which routine was essentially this one. First, we have to choose a central density, for example, whole C. We can call it this way. Whole C is the whole in the center of the star when R is equal 0. And from that, we can obtain the central pressure using the equation of state we have chosen. So after, we can set the central boundary conditions, N equals 0, and the conditions for B at the center of the star. And after that, we can use an integrator. And in our case, we use a Range-Kutner integrator in Python to integrate the system numerically, because analytically it's not possible to perform this integration. So we numerically integrate the system, and with that we obtain the mass, the pressure, the density energy, and B. And we have the structure of the star with that. The radius, the capital Y, the capital R of the neutron star is the value of R for which the pressure vanishes. So we have the pressure of the center of the stars, and we can perform the integration till the pressure becomes 0. That is the point when you say, oh, we have the radio of the star. So And the mass of the neutron star is then given by the function m, evaluated on this value found for the radium. So which whole C we are choosing? We can choose a lot of values for the central density. So each central density leads to different values for M and R of the star, the mass and the radius of the star. There is a very useful way to compare these models, these different theories of gravity, by using models of complex stars via sequence of models, which is specifically choose different values for the central density and see what happens with the relation between mass and radius and mass in the central density. And we obtain some curves, and we can identify what is the maximum mass for that equation of state that was chosen. So let's see some sequence of models for different equations of motion, and also different values of for C, because if you remember, the model chosen was that. So we have for each C, for example, 1, 2, 3, or -1s, we have a different model. So if you do that, we can obtain some curves. For example, here we have the left sequence of the mass. There are two curves, the dashed one and in this one, because there are different ways to perform the calculation of the mass, as I said before. But the important thing here is the black one is the general relativity when you have Xi equals 0. So if you change the Xi, for example, for negative values, we can see the maximum mass changing. So you have different maximum mass. So this example was made using polytropic with this index. Here we have the same idea, but with mass and R. And we can see general relativity here in this black curve. So using different values for Xi, we have different behavior. So here we have another polytropic with a different index. So here, yeah, Xi equals 0, we have general relativity again, and we can easily see the maximum mass for the general relativity. And if we change the Xi value, we can easily see that the maximum mass is graded. Okay, here we have a result using realistic equation of state. No, realistic is the following. No, here we are still using, we are still using the polytropic. But here we have this line, which represents the Butch-Dow limit. So we know from general relativity that the compactness of the stars cannot be greater than this value, even with different equation of states. Anyway, so we have always this limit. But with different model, we can reach compactness greater than that. So next slide, we have the result using realistic equations of state, and there are a lot of them. And we use this one named soft and stiff. There are two kinds of realistic equation of state. There are more. We have used three different types of realistic one. And here we can see clearly the behavior of the curve with c equals 0, which is equivalent to general relativity, and changing the value of c, we can reach bigger masses for the neutron star. Here we have the units, the proper units, solar masses and kilometers. In conclusion, it's possible to model this kind of stars using these distortion models without any perturbative approach, but we see in the literature many authors consider perturbative approach because the equations are very cumbersome to deal with. But if you use the conservation equation, we can make the problem easier to deal with. We have considered both polytropic equation of state and realistic ones, but it's essential to consider the realistic ones because with it we can constrain or even eliminate some candidates to equation of state, because when we confront the results with the observation, we can say, oh, this equation of state doesn't describe the reality. So it's important to always to apply these models to realistic equation of state. So we can see that different equation of states have difficulty to explain neutron stars with mass greater than 2 solar masses in GR. And it's interesting to see what the different alternative gravities can provide in this subject. So we analyzed that with this specific choice of f of t, but we are working on more general f of t. For example, with a power, not quadratic power, but with beta power arbitrary. So we can change that model we are considering. We could see that for a realistic equation of states, Kc less than 0 makes the maximum masses greater as compared to GR. So if we want to describe neutron stars with greater mass, we can use these models with negative Cs. Here we have some of the papers we have published in this subject. And this last one is one about this example I said. Let me go back here. If we consider f of t equals t plus c to the beta power, where beta is any number, we can look at a scenario more general. So we are doing that, and the work is here on archive here, and we are working some another properties and how can I say aspects about this theme. And that's it. I would like to thank you.
Thank you, Hemily, for the presentation. Is there any question? I would like to know, Emily, with the current results that you obtain, were you able to compare with some specific objects, some data, and see if actually some of those complex objects that were not completely identified, not completely in agreement with GR, were you able to explain them, of course, within the equation of state that we are assuming using FT theories of gravity?
Yeah, it's possible to do that, and I'm concentrating in principle to look at these models and using different equation of states, see how far we can go changing the models. But of course, when you look at some of these results, we can say, oh, this kind of equation of states doesn't describe the reality, because we know that, for example, there are greater mass for neutron stars we already observed. So we can really do out this kind of equation of state. And also there is the problem of the stability. So we are going to study this. So we have to study if the equation of state describe is stable stars, neutron stars. So from that we can eliminate another ones and compare with the data and say, oh, it's a good one, because determine the equation of states is a big problem in this sense, in this subject.
I see. So it's more like really not really matching the model to the data, but rather the inverse process.
Yeah. I don't know if the opposite can be done. I think so, but I don't know much about that.
I see.
Okay.
Thank you.
Thank you.
Any other? So I actually have another one. In the realistic equation of states, were you considering the transition of phase inside the neutron star? Is there this possibility?
I don't know, because this equation of state we can have them from the database, which contains a lot of kind of equation of state, and they came from deeply study of nuclear physics and a lot of things that I don't know about. So I'm just an user of this equation of state, but
I see.
yeah, but I don't know how they can obtain it.
Okay, because my doubt was in case you're assuming a phase transition inside your neutron star, since you said that you were using the continuity equation to simplify your computation.
Okay. Yeah.
In that case, with the phase transition, also the continuity equation will be
yeah, because in this case we are dealing with stars in hydrostatic equilibrium. So
I see. Okay.
If you change that, I really don't know.
I see. Thank you.
Thank you.
Okay, so if there are no other questions, let me thank you once more, Emily, for your participation, your presentation. It has been a pleasure.
Me too. For me too.
Is there a question? No. Oh, sorry, it seems not. So thank you once more. As I told before with Mark, feel free to follow up and participate to the other presentation. Right now we're gonna have a break, and we're gonna come back at 10:45 a.m. Brazilian time with a talk by Professor Davi. So
Yes.
yeah,
Yes,
he's already here in the room. Hi, Davi.
Hi.
So let's have a break and meet once again here. See you soon.